Field effect transistors. We saw that the output collector current of the transistor is proportional to input current flowing into the base terminal of the device, thereby making the bipolar transistor a current-operated device as a smaller current can be used to switch a larger load current. The field effect transistor, or simply FET however, uses the voltage that is applied to their input terminal, called the gate, to control the current flowing through them, resulting in the output current being proportional to the input voltage. As their operation relies on an electric field, hence the name field effect, generated by the input gate voltage, this then makes the field effect transistor a voltage-operated device. Field effect transistors can be made much smaller than an equivalent BJT transistor, and along with their low power consumption and power dissipation makes them ideal for use in integrated circuits such as the CMOS range of digital logic chips. Two basic classifications of field effect transistor, called the N-Channel Fet and the P-Channel Fet. The field effect transistor is a three-terminal device that is constructed with no PN junctions within the main current-carrying path between the drain and the source terminals. These terminals correspond in function to the collector and the emitter respectively of the bipolar transistor. The current path between these two terminals is called the channel, which may be made of either a P-type or an N-type semiconductor material. The control of current flowing in this channel is achieved by varying the voltage applied to the gate. As their name implies, bipolar transistors are bipolar devices because they operate with both types of charge carriers, holes and electrons. The field effect transistor, on the other hand, is a unipolar device that depends only on the conduction of electrons, N-channel, or holes, P-channel. The field effect transistor has one major advantage over its standard bipolar transistor cousins, in that their input impedance is very high, while the BJT is comparatively low. This very high input impedance makes them very sensitive to input voltage signals, but the price of this high sensitivity also means that they can be easily damaged by static electricity. There are two main types of field effect transistor: the junction field effect transistor or JFET and the insulated gate field effect transistor or IGFET, which is more commonly known as the standard metal oxide semiconductor field effect transistor or MOSFET for short. The junction field effect transistor has no PN junctions but instead has a narrow piece of high resistivity semiconductor material forming a channel of either N-type or P-type silicon for the majority carriers to flow through with two ohmic electrical connections at either end, commonly called the drain and the source respectively. There are two basic configurations of junction field effect transistor, the N-channel JFET and the P-channel JFET. The N-channel JFET's channel is doped with donor impurities, meaning that the flow of current through the channel is negative, hence the term N-channel, in the form of electrons. Likewise, the P-channel JFET's channel is doped with acceptor impurities, meaning that the flow of current through the channel is positive, hence the term P-channel, in the form of holes. N-channel JFETs have a greater channel conductivity, means lower resistance, than their equivalent P-channel types, since electrons have a higher mobility through a conductor compared to holes. This makes the N-channel JFETs a more efficient conductor compared to their P-channel counterparts. The relationship between the connections of a junction field effect transistor and a bipolar junction transistor are compared aside. The semiconductor channel of the junction field effect transistor is a resistive path through which a voltage VDS causes a current ID to flow, and as such the junction field effect transistor can conduct current equally well in either direction. As the channel is resistive in nature, a voltage gradient is thus formed down the length of the channel, with this voltage becoming less positive as we go from the drain terminal to the source terminal. The result is that the PN junction therefore has a high reverse bias at the drain terminal and a lower reverse bias at the source terminal. This bias causes a depletion layer to be formed within the channel and whose width increases with the bias. The magnitude of the current flowing through the channel between the drain and the source terminals is controlled by a voltage applied to the gate terminal, which is a reverse biased. In an N-channel JFET this gate voltage is negative, while for a P-channel JFET the gate voltage is positive. The main difference between the JFET and a BJT device is that when the JFET junction is reverse biased the gate current is practically zero, whereas the base current of the BJT is always some value greater than zero. JFETs are therefore known as depletion mode devices. We can see that the most depleted portion of the depletion region is in between the gate and the drain, while the least depleted area is between the gate and the source. Then the JFET's channel conducts with zero bias voltage applied, that is, the depletion region has near zero width. With no external gate voltage, VG equals 0, and a small voltage, VDS, applied between the drain and the source, maximum saturation current, IDSS, will flow through the channel from the drain to the source restricted only by the small depletion region around the junctions. If a small negative voltage, minus VGS, is now applied to the gate, the size of the depletion region begins to increase, reducing the overall effective area of the channel and thus reducing the current flowing through it. A sort of squeezing effect takes place. So by applying a reverse bias, voltage increases the width of the depletion region, which in turn reduces the conduction of the channel. Since the PN junction is reverse biased, little current will flow into the gate connection. As the gate voltage, minus VGS, is made more negative, the width of the channel decreases until no more current flows between the drain and the source, and the FET is said to be pinched off, similar to the cutoff region for a BJT. The voltage at which the channel closes is called the pinch-off voltage, VP. In this pinch-off region, the gate voltage, VGS, controls the channel current and VDS has little or no effect. The result is that the FET acts more like a voltage-controlled resistor which has zero resistance when VGS equals 0, and maximum on resistance, RDS, when the gate voltage is very negative. Under normal operating conditions, the JFET gate is always negatively biased relative to the source. It is essential that the gate voltage is never positive, since if it is, all the channel current will flow to the gate and not to the source. The result is damage to the JFET. Then to close the channel, no gate voltage, VGS, and VDS is increased from 0. No VDS and gate control is decreased negatively from 0. VDS and VGS varying. The P-channel junction field effect transistor operates exactly the same as the N-channel above, with the following exceptions. 1. Channel current is positive due to holes. 2. The polarity of the biasing voltage needs to be reversed. The output characteristics of an N-channel JFET with the gate short circuit to the source is given as. Because a junction field effect transistor is a voltage-controlled device, no current flows into the gate, then the source current, IS, flowing out of the device equals the drain current flowing into it, and therefore, ID equals IS. The characteristics curves example shown aside shows the 4 different regions of operation for a JFET, and these are given as ohmic region. When VGS equals 0, the depletion layer of the channel is very small and the JFET acts like a voltage-controlled resistor. Cutoff region. This is also known as the pinch-off region, with a gate voltage, VGS, is sufficient to cause the JFET to act as an open circuit as the channel resistance is at maximum. Saturation or active region. The JFET becomes a good conductor and is controlled by the gate source voltage, VGS, while the drain source voltage, VDS, has little or no effect. Breakdown region. The voltage between the drain and the source, VDS, is high enough to causes the JFET's resistive channel to break down and pass uncontrolled maximum current. The characteristics curves for AP channel junction field effect transistor are the same as those above, except that the drain current ID decreases with an increasing positive gate source voltage, VGS. The drain current is 0 when VGS equals VP. For normal operation, VGS is biased to be somewhere between VP and 0. Then we can calculate the drain current, ID, for any given bias point in the saturation or active region. As a side note that the value of the drain current will be between 0, means pinch off, and IDSS, means maximum current. By knowing the drain current ID and the drain source voltage VDS, the resistance of the channel, ID, is given as a side, where GM is the transconductance gain, since the JFET is a voltage-controlled device, and which represents the rate of change of the drain current with respect to the change in gate source voltage. Like the bipolar junction transistor, the field effect transistor, being a 3-terminal device, is capable of 3 distinct modes of operation and can therefore be connected within a circuit in one of the following configurations. Common source configuration. In the common source configuration, similar to common emitter, the input is applied to the gate and its output is taken from the drain as shown. This is the most common mode of operation of the FET due to its high input impedance and good voltage amplification, and as such common source amplifiers are widely used. The common source mode of FET connection is generally used audio frequency amplifiers and in high input impedance preamps and stages. Being an amplifying circuit, the output signal is 180° out of phase with the input. Common gate configuration. Common gate has a low input impedance but a high output impedance. This type of FET configuration can be used in high-frequency circuits or in impedance matching circuits where a low input impedance needs to be matched to a high output impedance. The output is in phase with the input. Common drain configuration. In the common drain configuration, similar to common collector, the input is applied to the gate and its output is taken from the source. The common drain or source follower configuration has a high input impedance and a low output impedance and near unity voltage gain, so is therefore used in buffer amplifiers. The voltage gain of the source follower configuration is less than unity, and the output signal is, in phase, 0° with the input signal. The Jfet amplifier. Just like the bipolar junction transistor, JFETs can be used to make single-stage class or amplifier circuits. With the Jfet common source amplifier and characteristics being very similar to the BJT common emitter circuit. The main advantage Jfet amplifiers have over BJT amplifiers is their high input impedance, which is controlled by the gate biasing resistive network formed by R1 and R2 as shown. This common source amplifier circuit is biased in class A mode by the voltage divider network formed by resistors R1 and R2. The voltage across the source resistor Rs is generally said to be about 1/4 of VDD, but can be any reasonable value. The required gate voltage can then be calculated from this Rs value. Since the gate current is 0, Ig equals 0, we can set the required DC quiescent voltage by the proper selection of resistors R1 and R2. The control of the drain current by a negative gate potential makes the junction field effect transistor useful as a switch, and it is essential that the gate voltage is never positive for an N-channel JFET, as the channel current will flow to the gate and not the drain, resulting in damage to the JFET. The principles of operation for AP channel JFET are the same as for the N-channel JFET, except that the polarity of the voltages need to be reversed.